Okay, so we're still looking at conservation of momentum, but unlike the separation of objects we had before where objects weren't moving in the beginning, now we have objects that are moving before a collision and they're going to be moving after. So our objects are going to collide into one another somehow and continue to move. Okay? A few kind of important notes for this. If you have a scenario where your objects are moving together after the collision, like they stuck together somehow, maybe with Velcro, or maybe they were like clay and they kind of smushed together, then if an object sticks to another one after a collision, they're going to have the same final velocity, and therefore we can consider them to be one mass that is combined together. Okay? We'll see an example of that in our practice problems when we get there. If they don't stick together, though, if they bounce off, or if like one hits the other and the other just like moves away, then they're going to be separate objects, M1 and M2, and they could have different velocities. Okay? So let's take a look at an example here. In our example, we have two gliders, and when we talk about gliders, we're not actually talking about hang gliders going through the sky. In the world of physics, in labs, there is something called a glider track. It's basically an air hockey table. It's just an air hockey table where along it you can slide these little gliders. They float on the air, and you can bump them into each other. Okay? So what it really does is it allows us to have a frictionless environment or a near frictionless environment to deal with. If you've ever played air hockey and the little hockey puck is floating on the air and you take a second hockey puck and move it in, that's what we're doing here. Okay? We just have two things on an air track moving along. Actually, getting your hands on one of these is a little expensive because the glider tables themselves are expensive, and then you need the air compressor, and that sucker makes a lot of noise. So we don't have one here, but if you see one in your life, this is what we're talking about. Okay? So we've got two gliders, or two little floating hockey pucks, on this frictionless air track. And we're going to draw two pictures here. We're going to draw a before picture, and we're going to draw an after picture, an initial and a final. So initially, we have glider A. We'll just put an A here. It has a mass of 0.36 kilograms, and it's moving on the air track initially with a velocity of 0.95 meters per second. And we can call this V1, or we could call it VA, whatever, however you'd like to designate the different gliders. And glider 2 is also on this air track, or glider B. It has a mass of 0.72 kilograms, and it's moving in the same direction. But its velocity, initially, is only 0.45 meters per second. So you can see what's going to happen here. Glider A is going to catch up to glider B, and it's going to give it a little bump from behind. Kind of like that one time when I was driving my car, and then someone was looking at their cell phone and rear-ended me. What a day. Don't look at your cell phones when you're driving, people. Come on. So this is what's happening initially in our problem. On the final side of our problem, after the collision, after the bump, well, after the collision, glider A still has the same mass, and it's moving in the same direction, but it has a new velocity. Glider A's final velocity is just 0.35 meters per second. What we'd like to know is, what is the velocity of glider B after this collision here? What is that final velocity of the glider? Now, before we start getting into setting up our conservation of momentum equation, it's just a nice thing to think about from a physics standpoint. What do we think should happen in this problem? Should glider B speed up? Should it slow down? Or should it stay the same? Pause this video and come up with your little answer on that. If we take some thoughts about this, we might recognize that the velocity of the second object, VB here, on the final side, should speed up. You got bumped from behind. You should shoot forward a little bit. You should be moving faster. So we are hoping here to find a final velocity for the second glider, glider B, to be greater than 0.45 meters per second. So at this point, we have everything we need to set up our conservation of momentum equation. Remember, this is our very large equation where it's m1 VAI plus well, I guess these are MAs, MB VBI equals MA VAF plus MB VBF. Whew. That's that giant equation we have for the conservation momentum for two objects. But the nice thing about this equation, if we take a look at it, we know the mass of glider A, we know the mass of glider B, so those are good. We know A's initial velocity, we know B's initial velocity, we know A's final velocity, which only leaves this to be solved for. And since it's the only variable we don't know with a single equation, we are able to solve for it. This is something that can be done. Is it going to take us a little bit of work? Yeah, but it is doable. So let's try to put some numbers in and figure out what we have here. So we know mass of glider A is, what is that, 0.36. We know A's initial velocity is 0.95. We know glider B's mass is 0.72. We know its initial velocity is 0.45. This is equal to glider A's mass again, that's our 0.36. And since it's moving in the same direction, and I guess we're calling right to be positive, then this will also be a positive number here. So the final velocity of glider A is still going to be positive. It's 0.35 plus the mass of glider B again, 0.72, multiplied by that unknown final velocity for glider B. So that is what we are looking for. Whew. Okay, let's multiply some things together. Let's get some numbers. And then once we have some numbers, this will be a lot more straightforward. So 0.36 times 0.95 is going to be 0.342. 0.72 times 0.45 is going to equal, well, that's kind of weird, 0.324. Look at that. 0.36 times 0.35 is going to give me 0.126. So let's take these values, rewrite this equation so that we have them. So over here we've got 0.342 plus 0.324 equals 0.126 plus, and then the MV for glider B. So 0.72 multiplied by that glider B final velocity. If we add the 0.342 and 0.324 together, we're going to get the number of physics, 0.666. That's going to equal 0.126 plus 0.72 times VBF. And at this point, this kind of reminds us of like a y equals mx plus b. This is pretty straightforward. We can just subtract 0.126 from each side. So subtract 0.126. So 0.666 minus 0.126 is going to give us 0.54, which equals 0.72 times VBF. And then we just need to divide by the 0.72. Whooshing! Divide by the 0.72. We're going to get a number less than 1 here. But that's okay, as long as it's greater than that 0.45 we had initially. So 0.54 divided by 0.72 gives us 0.75 meters per second. Which, hey, that is faster than the 0.45 we had. Our second glider, when it got bumped from behind, it did speed up. That's what we see here. So it's a great way to solve this problem. But a lot of this work that we actually did, a lot of it was just like some algebra. The actual big work was drawing ourselves a picture at the top. Once we had that picture, it was just a matter of shoving things into that giant equation and then kind of working things out and making sure that we get ourselves to our correct answer of 0.75. So the actual physics here is very small, and then it's just a matter of doing some mathematics. Now, this equation and the kind of answer could have changed a little bit if we change some things here. If glider B was at rest before the collision, then its initial momentum would have been 0, because in that case, this initial velocity would have been 0, and all of this would have gone away. So if glider B is at rest, changes the problem slightly. If glider B was moving in the opposite direction before the collision, then things change a little bit as well. Looking at our equation, instead of having a positive 0.45 for the velocity, if it was in the opposite direction, that would just be a negative. We'd still work everything out, but this would be a negative value we'd be adding to it. So our numbers would just change a little bit. Okay? We get a slightly different answer, but the setup is still the same idea. If the gliders stuck together after the collision, we get an interesting feature to occur here. If they stick together after the collision, then what would happen is we actually wouldn't know either of their final velocities, right? We wouldn't know what A's final velocity was either. But what we would be able to say is that since they stuck together, they're moving together. And that means that glider A final velocity and glider B final velocity would actually be the same. And because of this, these would be like terms that we could then add together. So if we wanted to, if they stuck together, we could rewrite this final part as 0.36 and 0.72 adding together to get 1.08 multiplied by the final velocity of the carts, both gliders together. But we didn't have that in this problem, so we didn't need to worry about it. But if we did, it could change like that. And if glider A stopped after the collision, then that A final velocity would be 0. All that momentum would be in glider B, and we could solve it the same. So there's a lot of different ways to set up these problems just from the picture, but in the end, the big equation we're going to be using is the exact same for all of them, because we're all in a line here, and we can just work out that algebra as we go along. Things do change a little bit if you have ricochets. You have one object strike into another and kind of deflect at an angle, but everything we're doing at this point is just objects moving back and forth just to the left and right. It allows us to use this equation and not have to worry about vector addition. So with that, this problem is finished. We'll be taking a look at a few examples in a later video, but until then, adios and take it easy.